Okay, so let me clarify one important thing that I think I didn't give a right explanation in the last class. I've sent out an email, but just for the sake of completion, let's do this. So when we are discussing this, we said that this is M1, this is M2. But we said that if these capacitors C1 and C2 are infinitely large, right? These are infinitely large. If, for example, if C1 is infinitely large, then this node voltage cannot move. It will be holding a DC value corresponding to whatever the quiescent was, regardless of there is a signal swing or not, right, at the input. So now if there is a signal swing, this is held constant, which means this is Vi. This current of GM2 times Vi will flow through M2. And naturally, this will flow through this. And the path that the current is supposed to take is back, right? So because ultimately we know all these grounds are connected together. So the path the current that will take is this. Now, obviously, there was this question, rightly so, that this node, when the current moves, and if I assume that this is ground, so this node will move. Right? Since this node moves, this node moves. These are the same nodes. So what will happen? A corresponding current, if I assume this to be V naught, a corresponding current of regardless of the direction, let's say this is GM1 times V naught, will get induced in M1. But what is the direction of this current through M1? This direction of the current through M1 will be this. Right? Because essentially what you are seeing is this current will the current that comes out of the drain source has to flow into the drain, right? And in the drain, it sees a short circuit. It sees an incremental short circuit. So which means that it has to come through this way, which means this has to go through this way, which means it has to circulate through this way. Right? So the current that will be induced because of the excursion of voltage at V naught will remain within that local loop of M1 and the capacitor, right? And this voltage will still remain GM times Vi times R minus because of the way the current direction has been shown. Okay. Any questions? No? Okay. So I had talked about one more circuit in the last class for those of you who might not have seen. I will give an assignment where we will be analyzing that in more detail. But I would like to move ahead with something with the next part of the course, and that is as follows. So we have been dealing with control sources since ESC 201 and this course also. And a transistor, as we saw, a transistor if I am applying a voltage between the gate and the source, and I'm observing the current into the drain, what type of control source is this? If this is my input, this is my input, and this is my output, it's a voltage control current source, right? Great. So this is a voltage control current source. This is a VCCS. And in order to figure out whether any contraption, right? So let's assume that I have any contraption. I have input port, I have output port. This is input, this is output. How will you figure out, what experiment will you do to figure out whether this is a voltage control current source or current control current source or any one of the four sources? In other words, what I'm saying is, when I say that it's a voltage control, right? So let's say I have VCVS and I have an input and I have an output. So what experiment will you do to figure out whether the stuff inside the box is a VCVS or a CCVS or one of the four sources? Let's assume I want to figure out whether it's a VCVS. What experiment will you do, or what characteristics of this network N will you be looking at to figure out whether it is what type of control source? Correct. So, but then you will require, that's the fundamental way of going about it. So you will be plotting the voltage at the, let's assume the input side. When you say you will be plotting the voltage at the input, what do you mean?
So I will be plotting the characteristic where on the y-axis I will take the output voltage, on the x-axis I will take the
okay, so okay, I understand now. So you are saying I will do this. So this is V naught, this is VI, and then what will you do? Okay, so I tell you that this is this type of curve, let's say.
So yes, it is dependent upon input voltage.
Right.
Voltage dependent.
Yeah, but I mean, it can be dependent upon input voltage regardless, right? I can have an input current, and the current can induce a voltage, and then it becomes dependent. The output voltage becomes dependent on the input voltage, but the input is a current source. So then, can I say it's a voltage control voltage source?
Similarly, we are inducing input voltage via
Current source.
Meaning if there is any resistance.
Yes.
Then directly input voltage.
Right. So then why do we have these four sources, right? So all of them can be, looks like modeled as a voltage control voltage source. Because I have a voltage, I can get a current. I have a current, I can get a voltage, right? So what is so special? So let's look at the output side. That might be easier. When I say something is a voltage source, what does it mean? If I say something is a voltage source, right? The output side is voltage source. Input side is a control source, right? Input side is voltage control. Output side is a voltage source. Let's concentrate on the voltage source part. Okay. So you have.
It depends whether the black box on the output
Yeah, so yeah, correct. So what he's saying is that it depends on whether the black box acts as a source to whatever has been connected to the output and what type of source, right? So that's essentially the question. If it's supposed to be a voltage source, what characteristics of this box do you need to check to figure out whether it's a voltage source or not? Right. So output impedance, right? The output impedance has to be very less than whatever you are driving, right? Ideally, your voltage source means your output impedance has to be 0. This is ideally, right? So if it's output impedance, like this is ROC.
Conditions for
correct.
relay load.
Yes. Similarly, if it's supposed to be voltage controlled at the input side, what do you expect the input to be? Input impedance to be, Rin to be for this particular network. But yeah, it should be ideally infinity, right? Because if you apply an input, if you apply an input voltage, a non-ideal input voltage for a voltage source, for example, then you would expect the entire voltage to appear across the port of the network, right? If the input, if Rin is not infinity, then there will be a voltage division between the source of the voltage source and Rin, right? So what I'm getting at here is that if you have a voltage source here and the Rin is not infinity, then the entire voltage will not appear at the input port of the network, right? So essentially this, you have an RL. Okay, so ideally your Rin should be infinity. Similarly, now if I say you have a voltage controlled current source, what will these conditions be? Your output should be infinity and input should be infinity, right? Similarly, if I have a current controlled current source, it's a current source at the output side, so ROC doesn't change. It's a current controlled at the input side now. So what do you think will happen? Rin should be 0, right? So if I have for example, if I have a current source which has an RS and it's connected to this network N, and I want all of this current to flow in, then this Rin should be 0, right? If Rin is 0, then only all the current will flow in, right? Current control means I want whatever absolutely high, largest value of current that I could have gotten from the source, that should go into the network. That's what current control means. And the maximum current that I can get from this source is I. If I is supposed to be going into the network N, then obviously Rin has to be 0, ideally, right? So similarly, if you have what remains current control voltage source, then Rin has to be 0 and ROC has to be 0, right? And this is an ideal scenario. And obviously, you will never get infinity or 0, which means you will always get some approximation, right? This is ideal. This is for table for ideal. So if I have to now make it realistic for cases where I have a real network which means that your Rin probably cannot be infinity and ROC cannot be 0, and I still want to realize a voltage control voltage source, right? So now you have to then consider inequalities, right? How big, how large, with respect to what relative things. So what will you look at? What should Rin be in realistic scenario? Rin should be much greater than RS, because ultimately you don't want any drop across the input port. Similarly, ROC should be, you cannot have 0. It has to be much less than RL. Similarly here, yeah, so in this case, in case of voltage control current source, what will ROC need to be? Pardon? In voltage control current source. Yeah, right. So it should be much greater than RL. Again, why? Because ultimately, if you have this is essentially the condition of Y22 equal to 0. Right? So because in the network, if you have a Y22 at the output port, then there will be, if there is a current that is getting pushed out, that current will divide between Y22 and RL, and you will not potentially get the maximum output voltage. You will put, or in other words, in this case, since it's a current source, I would see a division of the current at the output, right? Ideally, you don't want any division of the current at the output, which means that you don't want any output resistance, or rather you want infinite output resistance at the ports, at the output port of the network. Is that fine? I mean, we talked about this when we were introducing two-port network and we came to transistors, if you recall. Does that make sense? Doesn't look like. So let me, what was the two-port network? So you had Y11. I'm not drawing the feedback from the output to the input. You had Y21, V1, then you had Y22. This was the stuff inside the box. And we were connecting something here. Right? So if all this output current, all this current had to be drawn from RL or negative current flown into RL, then what was the condition of Y22? It should have been 0. That is equivalent to saying that network, this network N, right, not including RL, obviously, this network N should have an infinite output impedance. Right? If Y22 is 0, the output impedance ROC will be infinity. Right? And why do we need this? We need this because ultimately, if you recall, we wanted to ensure that whatever incremental current the network was generating should have flown into the load resistance. Right? Another way of thinking about it is, if you have when you are saying it's a current source at the output, right? You are saying that it's a current source at the output. Now, forget about the controlled part. Let's assume it's a current source at the output, and you are looking into this output side, and you know it's a current source, which means this is what it is supposed to be. Right? Then would you want an ideal current source or non-ideal current source? You want an ideal current source, but you know that ideal current sources are not possible. So which means that there will be an output impedance associated, there will be an impedance associated with the current source. And if you want all the current that the current source can generate to flow into RL, what do you expect? What do you want this ROC to be with respect to RL? Much greater than RL, right? If ROC is infinity, then obviously you don't have to bother about inequalities. Regardless of the value of RL, your block will be able to push out current into RL. But if ROC is not infinity, it's a finite value, but yet let's assume a large value, then what is large? That large has to be, ROC has to be much, much larger than RL. It is only then the entire current from the block will be flowing into RL, and that current will be independent of the value of RL. Right? If voltage is the voltage that you are seeing at the output node is independent of RL, then it's a voltage source. If the current that you are drawing from the network is independent of RL, then it's a current source. That's the definition, right? If the current changes, if you apply RL, then it's not a current source. It's something else. If a voltage changes, if you take a battery and you observe the voltage, and you keep on changing the output resistance. For example, you connect one LED, you connect 5 LEDs, you connect 10 LEDs, and you see that all of them are shining as bright. Then which means the voltage across that LED stack hasn't really changed. Which means that regardless of whatever you have connected, right, across the voltage source, regardless of whatever you have connected, the voltage source is able to is able to give that voltage regardless of whatever load conditions you have applied at the output of the source. So as far as voltage source, I assume that is easy to understand, easy to visualize. In terms of current source, the same thing in all the definitions go with respect to current. All the currents should flow into RL regardless of the value of RL. Which means you change RL, you don't want any current division. I mean, in reality, there will always be a current division, right? So in reality, this current is IOC, or in this case, let's say ISC. So what will be the current flowing into RL? The maximum current that could have flown in times ROC by. Now, if you can ensure that ROC is much greater than RL, if you can ensure this inequality, then you can see that your IRL becomes equal to ISC. Now, this is independent of the value of RL. Okay, then it becomes a current source. It becomes a good current source. Again, go back to that tutorial question that I had, tutorial 2, I think. Black box, what is it? Okay, so if this is the case, then everything else will follow. So if it's a current control current source, then Rn has to be much less than Rs. ROC has to be infinity, means ROC has to be much greater than RL. And in this case, ROC has to be much less than. So these essentially are the conditions that you need to satisfy. And when we did the source follower, right? When you did the source follower, that is, we said that we have a net circuit which was something like this. So what type of source was this out of these four? If you can ensure that GMRL is much greater than 1. Out of these four, what type of source is this? What about the input side? Yes, so it's a voltage control source. Output side? Yes, right. It's a fairly the same voltage. Yes, because it's fairly the same voltage because the output impedance is how much? The ROC of this network is how what? Looking into the source of the transistor, you can work it out and tell me. Not really 0. It's 1 over GM, right? It's 1 over GM. So if you can ensure that 1 over GM is much lesser than RL, or RL is much greater than 1 over GM, which means this condition, if you can ensure this, what are you ensuring? Its voltage will be constant, right? Approximately equal to VI. And that's what the math told us, which means that this is a voltage controlled voltage source, right? A transistor in its own, right? If I just take a transistor and let's assume this is bias in saturation and I have applied incremental VI, and I'm not sketching the biasing network, and this is connected like this. What type of source is this? Input side is voltage controlled because input impedance is infinity. Output is a current source, right? Yeah, so this is a voltage controlled current source because in this case we have assumed the output impedance to be infinity, right? So let's turn our focus to this stuff, this current controlled current source. Yeah.
So on the top we have the 130 volts, on the bottom we have current to clear stored. Those two parallel will be
Yes. Right. Yes.
So instead of current source, if there was another resistor RS, then it would be 130
parallel RS, correct. Yes. Right. And in fact, sometimes you make circuits like that. When you don't have, let's say you cannot afford a current source, right? I'm sorry about this, might be an emergency. Give me a minute. Hello. Yeah, so sometimes you cannot have a current source, you put a large resistor or some sort of resistor, then obviously the inequality will change. In that case, whatever looking in output impedance will be 1 over GM parallel. The resistance that you have put in place of current source has to be much lesser than RL. Okay. So let's turn our focus to this CCCS. So when you have a CCCS, what are we trying to, when you are trying to build a CCCS, what are we trying to do? We are essentially saying that I have a incremental current source, let's say I in, it's a non-real source, which means that I have a resistance RS associated with it. And the goal is to drive an RL. Goal is to drive an RL and ensure that all of I in goes into RL. Now you can readily see if RL and RS are comparable to each other, that's not possible, right? For example, if RL equal to RS, then obviously the current that will flow into RL will be half of I in, okay? And that, let's say, is not something that we want, which means that we need to put something here in between so that I am able to push all of I in into RL. Okay, so that's the problem statement, right? So we need to put something in between. Essentially, we need to put a current buffer. The voltage controlled voltage source was a voltage buffer, right? The source follower was a voltage buffer. We wanted the entire voltage of the input to go to some load RL. We had to put something in between. So we put a voltage buffer. Now we want to do the same thing with respect to current, which means we are trying to put a current buffer. So what will be a current buffer? So I have an RL. So looking at the table that we just saw, what do you think? If I have to put some network here, and I want all the current to flow into RL, so what should be the input impedance? It should be 0, or it should be very less with respect to RS, and whatever very less should be designer controllable. RS and RL sometimes are not designer controllable. It is given by the specifications, right? The designer controllable stuff are inside the box. So given that you know how a transistor works and you know what the impedance of a transistors are, can you tell me what am I looking for here in the incremental sense? I will put the full-blown transistor later. So in the incremental sense, which terminal of the transistor am I looking at if I want a low resistance? Source, right? Looking into the source is 1 over GM. And if I can increase GM sufficiently, then I can, in principle, lower the resistance looking into the terminal. Correct? So if I have, let's say, a transistor whose source is this, drain is this, gate is this. I know that this is GM times VGS is the relationship. So if I connect this here, and looking in impedance is 1 over GM under what condition? What should be the gate when I'm saying that looking in impedance is 1 over GM? Pardon? So what I'm saying is you have this contraption. And I'm saying that looking in impedance R in is 1 over GM. What am I essentially saying? You cannot do anything with the source. What is the gate condition? Is the gate connected somewhere? Is it shorted? Is it floated? It's shorted. Incrementally, it should be shorted, right? So gate should be short circuit incrementally. And where should so if this is the case, right? If this is the case and something, let's say, is connected at the drain, it's not open. Let's say something is connected. Right? So what fraction of the current will flow in? Or rather, yeah, so now you don't even have to go into the fraction. You can just tell me what proportion of the current I in will go in. They essentially mean the same thing. This will be I in times something or entire I in will flow in. The impedance looking, right. So the input impedance is 1 over GM. So the current that will flow in will be IN times RS by RS upon 1 over G. So what condition needs to be satisfied to ensure that the entire IN flows in? So the condition that you need to satisfy is RS should be much greater than 1 over GM, or in other words, GM RS has to be much greater than 1. So if you can ensure that, right, this is possible to be ensured because GM is in your control, right? GM is a designer controllable variable. So you can choose your GM in such a way that GM times RS is much greater than 1. Then all the current that you could have extracted from the current source, the maximum current that you could have extracted from the current source will flow into the transistor. Now, if that is the case, if this current flows in, this current also has to flow out, right? Nowhere it cannot go anywhere else, which means this current that is flowing out is almost equal to IN. And this current that it is flowing out, is it dependent? I mean, is it dependent on the output resistance? Let's assume I choose to connect this resistance RL here. If I change the value of RL, will the value of IN change? It will not change, because the output impedance of this is infinity, right? Your ROC is infinity. It's a voltage controlled current source. Looking in this impedance is infinity. Correct? Which means that I can simply connect that RL at the drain, right? If I simply connect that RL at the drain, I should be able to push in all the current of IN into RL. Now you keep on changing RL, it doesn't matter. It will always get the value of IN. Yes. Pardon? Right. Not necessarily, right? So he's okay. So let's. Yeah, okay. So let's look at it, right? So let's look at it. If I understand your question, you are saying that how can I say output impedance is infinite when source is not shorted? The source is not open, right? Okay. Okay, so let's look at it, right? So let's say incrementally this is grounded. So let's say something is connected here. I don't know what. Okay. And under the condition that there is no feedback from drain to source, drain is as is, and let's assume it's biased, right? I'm only interested in the incremental sense. What will be the output impedance? How will I know? So I will apply a test voltage. Correct? And I'll try to figure out the test current. Correct? So what will be the test current? Let's assume I have a test current, I test. Okay, so this I test will flow. And if I have an impedance here, let's say some R, it will generate a voltage of I test times R. Correct? And then, which essentially means that it's inducing the source voltage, which means the GM will induce a current, right? What will that current be? This current will be GM time, I mean, negative, but I am changing the current direction and saying this will be GM times I test times R, right? Because VS is I test times R. Correct? So if I do a KCL at that node, what do I get? GM times I test times R minus I test times R is equal to 0. Which means I test is equal to 0. Right? So which means you have applied a voltage source and you are not getting any current, which means the output impedance is infinite. Yes. It should not be surprising because even let's assume the load is 0, right? Let's assume the load is 0, which is source is grounded. Then also, what is the output impedance? Yeah, Vs is 0, but what is the output impedance looking into the drain? What is the impedance of the transistor looking into the drain? Infinity, right? So now I am, by putting something at the source, I am even making it worse, right? In the sense that I am adding extra, right? So it should not become finite now. Correct. So essentially, I mean, that's why they're looking into the drain of a transistor, you have infinite resistance, ideally, right? Okay. So now if you are convinced that this is the contraption in the small signal sense, right? We have to figure out how to ensure that the circuit gets biased when I put actual transistors in, right? This is the incremental picture. So I need the biasing picture also. I need the total picture. So what is the thing that I need to do now? I need to replace this GM with a transistor. So what should I do? So I have this incremental I in RS. Instead of GM, I replace the transistor. Incrementally, the gate was shorted, which means in absolute sense, it will be biased with some constant voltage, right? So I will have some constant voltage. I had this load RL here. Incrementally, once other side of the load RL was grounded, in absolute sense, it has to be some voltage. Okay. And incrementally, I was planning to connect these two nodes, right? But if IN is an incremental current, that is, it has 0 DC value, then I cannot do that, right? If IN has a 0 DC value, it's an increment. Let's assume IN is a sinusoidal current source, right? Then if I connect it directly there, the transistor will not get biased, right? So I need to bias the transistor. So which means I cannot directly connect it. That's the first thing. And if I cannot directly connect it, which means I have to ensure that transistor is biased in some way, right? So what should I do? How should I ensure that how do I set up the transistor in such a way that I have some transconductance GM? But source I have not yet connected to anything, right? Can I ground the source, for example? If I ground the source, some current will flow and it will set up some GM. Correct? But now how do I connect my incremental input to the source? Okay, I use a capacitor. But now where will this incremental current choose to flow? It will choose to flow into the ground. It won't go into the GM. Correct. So how do you keep a DC value of current? By putting a DC current source, right? Exactly. So you put a DC current source, right? You put a DC current source. So in the incremental sense, this current source will become ground to open, and all the incremental current will flow into the GM, right? So current control current source. Yes. 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 Right. So if this works and you can ensure that this current, whatever I naught, is such that it sets up the GM in such a way that the 1 over GM is much lesser than RS, then this will behave like a current controlled current source. Right? Make sense? So note that it's the same circuit, right? If I apply an input here and you observe here, then it becomes a voltage controlled voltage source. If I apply an input here and observe it here, it becomes a voltage current controlled current source, right? It's essentially the same circuit. So that's why a transistor is extremely versatile. Yes. Okay, so why don't you tell me, instead of I naught, is there any other possible solution? So let's start off with this, right? If I have to set up a current I naught, I can as well do this. Correct? DC condition will be satisfied. But now what will happen to this I in? This I in will now flow here. It will not go upstairs, right? It will not go into the transistor. Since it will not go into the transistor, my input impedance is fine. I have been able to satisfy, but it's of no use. It's going into an actual short. I would want it ideally to go into a virtual short. Correct? So why did I make that statement? So if ideally in the incremental sense, this current is 1 over, this impedance is 1 over GM. If 1 over GM is much, much less than RS, right? Then I can say that this becomes I in RS, some resistance Rin, which is much less than RS. Correct? If Rin is much less than RS, this voltage that will develop here is I in times Rin. And if Rin close is almost close to 0, right? So this voltage will be almost close to 0. Right? So you put in, you are adding a current, incremental current In, but you are not seeing any change in the voltage at that node. Right? You are putting in a current, but no change in voltage, which means it's a short. It looks like a short, but it's not an actual short because it's not going into a ground. It's a virtual short. Because by using some contraption, you have ensured that the impedance has gone down. Right? It is not gone down to 0, but yeah, in an extreme case, you can say that I'll make 1 over GM to be much smaller than RS. Then obviously this, you can assume that this is not moving as it would have moved if 1 over GM was not there. Okay. But coming back to his question, so putting a short circuit there will not suffice. Right? So what else can I do? Yeah, I can add a high resistor, or high resistor is essentially you are trying to mimic a current source. So yeah, I can as well put a current source. Right? Yes.
Can you also and apply this DC current source parallel to AC current?
Yes, you can do. In fact, if in some cases you actually do. For example, I think you have already done this in one of the assignments, in the sense that how do you realize this DC current source? Using a transistor, how do you realize the current source? You had a comment? How? Yeah, you just take a transistor in a common source configuration and stick it there, right? So this I can. So what is this I naught? This I naught is a current source, and I have not told you this needs to be a independent source. It can also be a controlled current source, right? A transistor is a controlled current source. If I put a transistor here and ensure that this is in saturation, and I apply VV2 such that the values of VV2 is such that this pushes in current of I naught, then this becomes a controlled current source. Correct? And coming back to his question, if I apply an incremental current voltage here, what will this current be? Now, to be I naught plus, if this is M1, GM1 times VI, right? So this is equivalent to saying, that I have I naught and I have GM times VI, which is IN. right? So I think this you have already done, right, in one of the assignments. So this particular configuration where you fix the gate voltage and you apply an input at the source and you observe at the drain, this is called common gate configuration. It's called common gate. So you saw common source, common drain, this is common gate. There is one more thing you can do, is also called current buffer. In addition to being called current controlled current source, right? So if you want a voltage buffer, you know what to use. Use a source follower. If you want a current buffer, you know what to use. You use a common gate configuration, right? So these are single transistor implementations of voltage buffers and current buffers. Okay. It's common gate because ultimately gate is shorted. Incrementally gate is shorted. Now, when you take any voltage, you essentially take it between that voltage, that node, and a short, which means the short is common, so gate is common to all. So that's why you call it common. Okay, fine. Any questions? Yeah, I'm not particularly bothered about that. I'll give you the diagram, or if you have to design something, you can put in that design, right? But this is something, if you go out and you talk to somebody and he asks you what is the common gate configuration, you should at least know what it is, right? It's a jargon, but sometimes jargons are useful. It makes you feel smart. Okay, fine. So before we end, by now you must be aware of the fact that, or if you are not aware, this must be bothering you, that how can a real transistor have an infinite output impedance, right? Nothing in reality is zero or infinity. This is approximately, you always model something, right? We model something as zero, we model something as infinity. They are this flip side of the same coin. So in fact, the transistor output impedance incrementally is not infinity. It's a large value. Again, large is a relative term, but it's certainly not infinity. And the reason it's not infinity is as follows. So if I go back to the transistor architecture or transistor layout, so a transistor, if you look at the drain, has infinite impedance, right? So what I'm saying is that it's actually not infinity, right? In reality, a transistor doesn't have infinite impedance. So we are trying to figure out why. So what was the genesis of this infinite impedance? The genesis of the infinite impedance was, there was a charge profile, and the charge profile became skewed as you kept on increasing the voltage at the drain. And it became skewed, it kept on becoming skewed till the charge went to zero at that drain channel junction. So the channel was pinched off. Since the channel got pinched off, we said that no more excursion of voltage at the drain will lead to increase in current. So which means the current got saturated. Since the current got saturated, my IDVDS plot look like this. So this was a flat line parallel to the y-axis, parallel to the x-axis. So obviously the conductance of this, that is the slope of this, is zero, which means output impedance got infinity. Incremental output impedance was infinity. Now, what I am now saying is that this is not the case. This is not the case because what actually happens is, after you have reached pinched off, and if you keep on increasing this drain voltage, right? If you keep on increasing this drain voltage, then the excess amount of voltage that you have gotten above this pinch of voltage, right? This is the overdrive. So what it does is it shifts this it shifts this charge distribution to the left slightly. It's not appreciable, but it's not zero also, which means that there is the new length of the channel. So this was the original L. The new length of the channel got reduced by some value delta L. Right? So if this happens, then you can model the new current voltage equation as L minus delta L times V over dry square. Okay. And this L minus delta L, I can do Taylor series and say this is W by L. This is approximately. And to a first order, I can say that delta L is proportional to VDS. Because cause of delta L was I had applied some VDS, right, on top of saturation voltage, and that moved the delta L. So the first order approximation, I can say this. So if that is the case, I can say this is equal to one plus some proportionally constant lambda times VDS. Okay. So now clearly you see there is a relation between ID and VDS, which was not there earlier. So this relationship, what this relationship does is this slope is not non-zero. So you have certain slope. It is not as high, as steep as linear region, but it's certainly not zero, right? So this makes your transistor a non-ideal current source, which means its Y22 is not zero. Incrementally, your Y22 is not zero. You'll have some Y2. Okay. Okay. So let's stop here. We'll start off from here in the next class.